All right, so the next piece that we're going to work on is the alternating series remainder. So the alternating series remainder is just a way to use the partial sum as an approximation for the actual sum of the series. And what it tells us is that the difference between the whole series S and the partial sum is bounded above by the n plus 1th term. So this difference, S minus S sub n, is denoted R sub n, where it's called the remainder. So let's see if we can use it to get an estimation for the actual sum of the given alternating series. So the first thing that we need to know, if we kind of peek back at the Theorem 915, S itself needs to be convergent. And just remember that we've done a lot of examples where we've demonstrated the convergence of a series without computing the value, the limit to which it converges, right? We've been kind of going through and saying, yes, it converges, or no, it doesn't. So now we're going to have to start off with saying, yes, it converges, and then do the estimation. So we require that it's convergent. And we also require that the sequence is decreasing. Once we have that, then we can use the approximation. So we need to first determine, so we want to show that our series converges. And so for this, we're going to use the alternating series test. So we have the form, right? It's in the form of an alternating series. And a sub n equals 1 over n factorial, which is positive for all n. So we have that. The next thing we need to do is we need to take the limit as n goes to infinity of 1 over n factorial, and that's equal to 0. So we have that. And then we need to show that a sub n plus 1 is less than or equal to a sub n. So that's going to be 1 over n plus 1 factorial less than or equal to 1 over n factorial. And that's definitely true because on the left-hand side, we can see the denominator is always going to be larger than that of the right-hand side. So we have that. So then the alternating series test tells us that this converges. The next thing that we need to show in order to use the remainder theorem is that a sub n plus 1 is less than a sub n. But we already showed this when we use the alternating series test. So we have that. And so now we've met the requirements and we can use the remainder theorem. So we're going to approximate the sum of this series by its first 6 terms. So that means what we're going to get is we're going to get that S minus S6, which we define as the remainder, R6. This has to be less than or equal to the 7th term. And so what's going to happen is that we're going to end up with an inequality. So first of all, S6, I definitely need more room. Let's see. So S6 is the sum from n equals 1 to 6 of -1 to the n plus 1 times 1 over n factorial. And so this is going to equal 1 minus a half plus a sixth minus a 24th. So I would just go through and write it out by hand. And then stick that into my calculator and let it produce the fraction for me. So 91 over 144. And then we also need to know what A7 is. So A7 is negative 1 to the 8th power divided by 7 factorial. So this is 1 over 5,040. So now that we have these two things, we're going to say that the absolute value of S, and remember we're trying to compute or get an estimate on S, minus, so S6 was 91 over 144, and that needs to be less than or equal to A7, which was 1 over 5,040. So from here, what we can do is we can create an interval. So we would get negative 1 over 5,040 is less than or equal to S minus 91 over 144, which is less than or equal to positive 1 over 5,040. And I'll add 91 over 144 to both sides. So solving for S, if you did an approximation, you would end up with 0.6317 for your lower bound and 0.63214 for your upper bound, which is a nice kind of tight interval that's going to give you a good approximation for S. Later, we'll see through other testing methods, I think in 9.6 possibly, that the real value is E minus 1 over E, which is approximately 0.63212. All right, the next example I want to do is figuring out how many terms we need to hit a certain margin of error. So I need to move some stuff. So here we're really just trying to find find n, capital N, such that the absolute value of your remainder is less than 0.001. So in order to do this, what we're really going to do is we're going to take R sub n, and we know that R sub n is bounded above by a n plus 1. And so if I just stick that in the middle, then I'll be sure to achieve this tolerance. So here I'm just going to use a sub n plus 1, and I'm going to solve the right-hand side of the inequality, and that will give me the appropriate n. So looking at our original series, we can tell that a sub n is equal to 1 over n to the 4th. Therefore, a sub capital N plus 1 is 1 over n plus 1 to the 4th, and we want to know what values of n is going to make this true. So I'm just going to flip both sides. So I'm going to get n plus 1 to the 4th, and if I flip, I have to change the direction, and the reciprocal of 0.001 is 1,000. So now I'll take the 4th root. So n plus 1 is greater than or equal to the 4th root of 1,000. So n has to be greater than the 4th root of 1,000 minus 1. And this is approximately 4.623. So we know that for n equals 5 and above, our remainder will be less than 0.001. So the answer is 5. And this is kind of how it shakes out.